Alright, so today we're going to start off with, as we will often do, with a little repeat and review from last time. They say that if a teacher repeats something many times, then students are more likely to get it. So let's see if that's true. Last time we did some vocabulary words. One of the vocabulary words that we learned was a binary operation. That's combining two numbers together. That's going to be a super important idea for our class. We're going to be combining by addition, multiplication, division, and subtraction, but more than anything, multiplication and addition. So the fancy name for that is a binary operation. We learned that last time. We also learned our famous sets, natural numbers. These are the ones you count with. Integers, that's them, and all of the ones that are negative counterparts. Although that story is not complete, I still have to tell you what the negative counterparts mean. But we'll come back to that. These are called rationals, the ones with a Q. Set of all fractions such that both numbers are integers, both numbers are in that list, but the bottom is not 0. That's how you read this. The set of all A over B such that A and B are integers, but B is not 0. In addition to some vocabulary words, we also learned our first two axioms. The addition table, which says we all know how to add numbers, natural numbers, and also the times table. In a nutshell, this is what we did last time. This is called a repeat and review. Okay? This is our R&R. And from here we will pick up and keep going with it. What we're going to want to do is add a couple more axioms. Every day we're going to try to add a couple more axioms. The lectures are going to be super easy at first, but incredibly important. You must know these axioms. Alright, so let's get on with it. What are we doing today? Today we are doing these axioms are called commutativity lost, and so let's do the first one. The main idea is that sometimes order matters. Not always, but sometimes order matters. Now let me explain what I mean by that. Let me get this pen here. And so sometimes order matters. So if I have 3 plus 5, would it matter if instead of doing that I do 5 plus 3? Let's check. I know how to do that because of the addition table. That's equal to 8. And I know how to do that because of the addition table. 5 plus 3 is equal to 8. So in this case, order doesn't seem to matter. I could do it both ways. 3 plus 5, 5 plus 3, same thing. But sometimes it does matter. For example, if I had 3 minus 5, we haven't explained that yet, but just go along with it for a second. Sometimes, some operations, the order may matter, and we'll see later that this actually matters a lot. You don't get the same answer if you take 3 subtract 5 versus if you take 5 subtract 3. So this may not be interchangeable, while these ones are equal. Whenever that happens, we have a fancy name for that. And let me explain the fancy name. It says if you take the 3 and then you have the 5 and you imagine that the 3 is going to commute that way. The 3 is coming over here and it's going all the way over there to where the 5 is, and the 5 is going to commute. It's going to commute that way. The 5 is going there. They commute. The 5 commutes over there. The 3 commutes over here, and you get that that's the same thing as the 5 plus the 3. Okay, that's why it's called commutativity. Commutativity property of addition. You got the addition sign in between here. The 3 commutes that way and the 5 commutes this way. That tells us, we can summarize this axiom by using the famous icon we made up for it. I made up for this icon. It says you have a plus there. Whatever number you have here goes over there. Whatever number you have here goes over there. This is the commutativity dance. If you ever want to be on a dance floor and you be hit, this is the commutativity dance. The things commute. And of course this one's for addition, but the same thing is true for multiplication. Again, a lot of these axioms come in pairs. You saw the tables, we had 2. One for addition, one for multiplication. Commutativity, one for addition, one for multiplication. What about subtraction and division? They're not that good. They're lesser operations because in those cases, order matters a lot. That's why we get 2. Addition and multiplication. We don't get 4. Alright. Let's see. Let's take a look at the multiplication version of that. See how that goes. Oh yeah, before we go on, I should emphasize a couple things. What it says is that you could, here, this is what it says. Let's say, it says that, whoa, I'm camera shy now. It says that if I have A plus B, that's the same thing as the A commutes here and the B commutes there. B plus A. That's what it says. Okay? But you also should note that a lot of these things are, while they may be true for some numbers, sometimes they're not true for other things. So it's important to indicate here what numbers does it apply to. Okay? Let me move this over here because that looks a little strange, right? So this one says A plus B is equal to B plus A. And we need to answer this question, what does it apply to? Well, it applies to, here, I'll make a little error here. It applies to natural numbers, check. It applies to integers, check. It applies to rationals, check. It applies to variables, at least the variables from our class, check. It applies to symbols, at least the symbols from our class, check. It basically applies to almost anything from our class. There will be some exceptions and we will point those out when we get there, but maybe not. Well, I'll tell you, we'll cross that bridge when we get there. For now, all of our numbers here and variables that represent these numbers, it works for all of them. That's different than the times table. The times table only applied to natural numbers. Same thing for the addition table. It only applied to natural numbers. These ones, they apply to all of our symbols. Okay? Alright. Now, what else do we have? Oh, let's practice it. So again, suppose I have, for example, let's see, suppose I have, for example, I'll practice it here. 3 plus 5. What is that equal to? Well, that's the same thing as 5 plus 3. Why? Commutativity law of addition, COLA. Okay, that's an example. Another example, I told you it worked for all the worked for fractions too, even if you don't know what a fraction is. 3 plus 1/2, is that the same thing as 1/2 plus 3? Yes, by commutative law of addition, by COLA. And if you want to be fancy, you can quote it using the symbol here. X plus y, is that the same thing as y plus x? Yes, by COLA. You can write it this way. All you did is move the x on that side of the plus and the y on that side of the plus. They commuted. Okay. Here, a couple more examples. What if I have 3x plus 5? Can I write that as 5 plus 3x? Yes. All you did is move the things around the plus. That's called commutativity law of addition. Okay. One more. What if I have 4 plus f of x? Is that the same thing as f of x plus 4? Yes, because all you did is use commutativity law of addition. And so the examples are pretty easy. You have a lot of flashcards to practice these. I think you're going to be okay, I hope. So let's clear the board here and let's move on to multiplication. So we have another story just like this one. It'll be nearly identical, except wherever you see plus, you'll have times, and so it'll be the commutative law of multiplication. Alright, so easy, let's do it. Can't believe I get paid to do this, but I do. Insane amounts of money. Alright, so commutative law of multiplication. Notice the symbol tells you exactly what's going to happen. You're going to have a times here in the middle. Whatever you have here will go that way, whatever you have here will go this way, and that's it. That's commutative law of multiplication. Let's get on with it. So what it says something very easy. It says that if I have A times B, that's the same thing as having B times A. Okay, that's what it says. You may wonder, well, what does it apply to? Well, let's take a look at that. It applies to, again, almost. Does it apply to natural numbers? Yes. Does it apply to integers? Yes. Does it apply to rationals? Yes. Does it apply to all real numbers? Imaginary numbers? Yes. Yes and yes. Variables? Yes. Basically, almost anything that we do in our class, it applies to them. Or symbols that represent any of our numbers, it works there. That's different again than the times table and addition table, which were limited to those guys only. This one applies to everything. terms, especially. We'll talk about terms in just a second. And could we practice that a little bit? Yeah, we could practice right now. Let's practice that. Why not? So for example, if I have, I'm going to practice right here. An example. Suppose I have 3 times 5. How could I rewrite that in a different way? It's the same thing as 5 times 3. The answer is yes, by commutativity law of multiplication. That was easy. Another example. Suppose I have 10 times x. Could I write that as x times 10? Yes, I could, by commutativity law of multiplication. That's my symbol. Actually, I like writing it. When I write the symbol, I don't like those brackets. So I'll write times. Yeah, the thing over here went that way. The thing here went that way. Another example. Suppose I have x times y times x. Oh no, we can't do that yet. That's 3 things. That's coming up in a second. Let's do a different example that we can do. If you have 2 items here, 4x, but it's grouped together, times 5. Now I'm looking at these as 2 items. Here's the times. The 5 could go over here and the 4x could go that way, and that would be the same thing as 5 times 4x. That would be good. That's by commutativity law of multiplication. It's simple. You have multiplication in the middle, and you have 2 items on either side. The one over there goes to that way. The one over here goes to that way. Goes to the other side. You could do this all day long. Maybe I'll just do one more. 0 times 5. What is that equal to? I don't know what it's equal to, but I know it's same thing as 5 times 0. And I know that because things can commute. It's commutativity law of multiplication. Okay? One more, last one. Pi squared times 7. Again, you may not know what those symbols mean, but it doesn't matter. It works for all the symbols in our class. Okay, so here's a times. You have a times here. You have some item on the left, you have some item on the right, and you have a times in the middle. These things can commute. So it's the same thing as 7 pi squared. Sometimes when you just have a bunch of letters or symbols, people omit that dot, and that's okay. It just means the same thing as multiplying. But the switch here, the commuting of the items was legitimized by your new friend here, the axiom commutative law of multiplication. Okay, alright, that's enough practice for us for the video. You can practice this a lot more on the flashcards. You'll be doing hundreds of these. Okay, alright, next we're going to add one more entry to our vocabulary list. New word for us. This one is a term. This one is incredibly important. Let's take some time to get to know what a term is. So what it is this term is a bunch of things being multiplied together. You can think about them as being glued together with times. So for example, if I have 3 times 2, that was a bunch of things being glued together with times, with a times in the middle. That's called a term. That's an example. Another one would be 3x. Even though you don't see the times there, that's because it's customary. Whenever there's no operation, the default one is times. That's called a term. If I have 3xy squared, I could have as many as I want here. They're all glued together with times, 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 times. Everywhere in between here, there's no operation. So that's called a one term. This is one term, this is one term, this is one term. Okay? Those are terms. A bunch of things being glued together with times. Okay, if that's a term, then let me think. You saw some examples. What would happen when you have? How do you get 2 terms then? Well, 2 terms would look something like this: 3x, that's one term, plus 5. Those are not glued together with times. Those are glued together with plus, so they're not called terms. That one right there is a term, and that one right there is a term, and so this is the plus separates a term. So this is called 2 terms. Another fancy name for 2 terms is often called a binomial. Binomial means 2 of them, 2 terms. This is an example of binomial. Okay, is that easy? So those are, I'll give you some more examples. Let me get back to this one. So we're going to do a lot of terms here. We could have 3x squared plus 4y to the 7th. Notice right there, all that stuff is glued together with times. There's no plus or minus. All that stuff is being glued together with times. There's no plus or minus, so that's called a term, and that's called a term, and the plus separates them. Terms are really only separated by pluses or minuses. You can think about those as bookmarks, separators. They separate all the things that are terms. Okay, those are terms. Those two terms. This is a binomial. This is a binomial. All right, now what about a trinomial? Could we get a trinomial? Well, how could you get three terms? Well, it's easy. You just have to have two pluses, because those are the bookmarks, and that would get you three terms. So the simplest example I could possibly think about would be 3 plus x plus y. You see, right there I have a plus. Right there I have one term. Then you have the plus, that separates it. Let me make a little here. That. The separators are the pluses. And also minuses when we get to them. 4x minus 4 plus pi x to the 7th. I scan this. I don't see any plus or minus, so all that stuff is glued together as one. This is one term. This is a minus, that partitions it, so you have another term. This is a plus, so that's another bookmark. So that gives me three terms. Those are often called, the fancy name for those, of course, is called trinomial. You can imagine why it's the trinomial, because you got three terms. Now the terms are going to be super important, because that's what we add. We always add terms. We don't add pieces of terms. Let me elaborate on that, because it's so important. I see this as a big problem always. So we should probably elaborate on it. Let's do this. Okay. So suppose I have 5 plus 20, right? You would never ever try to say, you know what, that's equal to 70. Well, you might if you're on something, I don't know. But the point is that you don't add the 5 and the 2 and say, oh, I got 5 and 2, that's 7, so I have 7 and a 0. We don't do this. How come we don't do this? Why is it that, let me see here. Why is it that this would be such a bad idea? Because the 2 is not just the 2 separable from the 0. The 2 is glued together to the 0. So this is one term. One term. You can't treat it as, we don't never ever add the 5 to a piece of a term. Never. We just don't do that. We add whole terms, not pieces of terms. Same thing is going to happen if you had something like this. Let's go back to yellow. What if I had 5 plus 2x? These two things are being glued together with a times in the middle. They're glued together. You would never ever say, you know what, that's got to be equal to 7x. Ignore the fact that the 2 is glued together to that x. It's the same kind of gluing that happens when you have a 0 next to it. It's a whole thing. You can't just add little bits of it. Same reason. That's why we don't add pieces of terms. This would be a very not good idea. You could do it if you're a trailblazer or a lost soul only. The rest of us, we don't do stuff like that. We add. The important thing to note here is we add terms, meaning that everything that is glued together with times goes together, all or nothing. We never ever add pieces of terms. That's a piece of term. We don't add pieces of terms. This is like a one whole item. You can't just break it apart for no good reason. Okay, we only add terms. All right, I think that will do it for us. Let's see what else we've got prepared for you. Let's clear this and summarize. Yeah, summarize. So today we learned the commutative law of addition, which says the A would commute that way, the A would commute that way, the B would commute that way, and so you get the same thing as BA. Today we also learned the commutative law of multiplication, which says the A commutes this way, the B commutes that way. And we learn what these apply to more than just the natural numbers, to all of our symbols from the class. We also defined the very, very important word. We added one entry to our vocabulary, term. That's super, super crucial. Collection of numbers or symbols or variables that are merged together with times. Okay, that's it. We're going to keep it simple. It's all you got to do today, but it's absolutely non-negotiable. You must understand this like your life depends on it. Okay, this is crucial. You got to understand these 3 ideas. If you do that, it's a good day. Come back and we'll do another one. We'll see you guys here next time. Peace.